We're going to be going through example 2 really quickly of what we did in class, and then we're going to do one more example just so that hopefully will help you as you're continuing into 4.1 over this long weekend. So here we go. We've got the function that I've rewritten, and writing it as a power function, we get to use the power rule. And that's just an easier way to differentiate. But you can use the quotient rule, and we should agree that this notation is telling me the instantaneous rate of change. And it's always a good idea to look at your function and understand that for this function, any value for x is in the domain except for plus or minus 1. So the focus of this lesson is we are hunting for extrema. And so this is a very important use for a derivative, is knowing that the derivative will tell me the instantaneous rate of change and that there are 3 places that we look, 2 of them being critical points where the derivative is equal to 0 and there's a sign change, and where the derivative does not exist and there's a sign change. So our critical points that we're going to find is where x is equal to 0, and that makes the derivative equal to 0. And the critical points are where the derivative doesn't exist, but what we find is that where the derivative does not exist is in fact where my function is not continuous. So my only critical point is at where x is equal to 0. So going back to what we did in class, is I put 0 on my number line and I'm analyzing the derivative. So this number line is just a way that I can organize information. I'm going to put in those spots at -1 and 1, and I'm just going to put an x right here because I know, or maybe I'll put a star there, that those are spots where the function is not continuous. And yes, we do know that those are vertical asymptotes. But what I'm doing is checking, and I want to know before, let me do this here, in this zone right here, what's true about the instantaneous rate of change? And to the right of that location of my critical point, what's true about the instantaneous rate of change there as well? So there may be extrema here at 0, but I must see if there's a sign change. So what we decided to do is we decided to check a value close to that critical point. So we checked at -1/2 and then checking again at +1/2. So on this interval, we're going to find by plugging in a half, and what I'm doing is I'm plugging in 1/2 for my input of the derivative, and I'm plugging in 1/2 there as well for the input. And so all you really need to do is to verify, is the derivative positive or negative? And so when I put in a negative value into the numerator, I get a negative value. And when I plug in a negative value into the denominator and I square it, and I take away 1 from it, I'm getting a positive number. So therefore, my derivative is going to produce a negative value. Let me fix that there. So when a derivative is negative, we know that the function must be decreasing. And then I'm going to check again at +1/2. So my numerator ends up being a positive value. And my denominator, squaring a positive like 1/2, I get a quarter. 1 minus a quarter is positive. Raising that to the 4/3 power is still positive. Multiplying by 3 is still positive. So on this interval, my derivative is positive. That means that my function must be increasing. So what you need to know in terms of readers when they're looking at your work, any of this work right here is really for your eyes only. And it's going to be really important that we explain what is significant about everything that I put where I analyze the critical point. So this function I know has f has a minimum value at x is equal to 0 because f prime of x is equal to 0 and changes from negative to positive. And that's really all you need to do to show the analysis of the function. So up here, what we did in class to get this critical point, and I know that I did in class, but it's really important that you show that you're setting that derivative equal to 0 and solving for it. So I wish I had more room to do that, but we had done that in class. Now I want to talk to you just really briefly about what we know from our studies in pre-calculus. So what I'm going to do is I'm going to draw the XY grid, and I'm going to put in my horizontal or vertical asymptotes rather at -1 and at 1. Now what we should know from pre-calc and calc is that the degree of the denominator is bigger than the numerator. So I'm going to go ahead and put in my horizontal asymptote like so. So what I know is in this zone right here, let me fix that. My function is decreasing from -1 to 0. And I know in this zone right here, my function is increasing. So what I could do is I could figure out the y-intercept. And so going back up to my function, I can plug in 0 for x, and yes, I am getting 1. So I'm going to go ahead and plot that point. So you may recall that rational functions can have interesting graphs. So I am decreasing, then I am increasing. And ironically, in my pre-calc class, this is what we're doing, what we did in fact last week. And then lastly, if I do test values in this region over here and in this region over here, I'm going to find that my ratio is negative. So no matter what my input, I am going to get a negative value. So I'm going to erase that, and I can't erase the other side, but I am going to draw that in, and that piece is going to look like so. So calculus is going to allow us to find where that minimum value is. Is it an absolute minimum value? No, we would call that a local minimum. So there are no endpoints. My domain is all reals. I'm able to use the calc to find exactly where that minimum value is. Alright, with example 4, we're going to do the same thing. We're going to be analyzing our function, and we are hunting for extreme values. So I am going to emphasize with you that it is important to know our domain for the function. So I'm looking at, we've got a composition function. I have a function and a function. And what's important to know about ln's, because they are related to exponentials, that what is inside the function must be greater than 0. So we need to look at what makes the input x. So what makes this ratio equal to 0 is 0. So simply you can multiply both sides by 1 plus x squared. But my answer to that for the domain is x has to be greater than 0. So once again, I do not have any endpoints, but we're going to be looking to see where y prime is equal to 0. We're going to be looking at where y prime does not exist. So let's find it. Do you know how to take the derivative of a ln function? And so I'm going to just write down here, if y is equal to ln of stuff, so that's u, then y prime is equal to u prime over u. And I'm just going to put that condition that u has to be greater than 0. So we've already done the work there. In terms of x, that means that x has to be greater than 0. So we need to know how to differentiate, again, my stuff. So using the quotient rule would make perfect sense. The derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. And so that's simply just a matter of using our notation for the derivative. So I'm going to erase a little bit here. Give me a second to do that, and then I'm going to go through those steps of differentiating a natural log. Alright, so I've indicated what my inner function is, and now I'm going to do the quotient rule. The derivative of the top is 1. I'm going to multiply that by the bottom, 1 plus x squared. Minus, now we're going to take the derivative of the bottom. So the derivative of the bottom is 2x, using the power rule. We will go ahead and multiply that by the top function, which is x. And all of that goes over the bottom squared. So there's the derivative. So now what we're going to do is we're going to take a minute to clean that up, and then I'm going to go ahead and write what the derivative is of the ln function. Alright, so I've cleaned that up, and there's my u prime right here. And there's my u right up top there. So what I'm going to do is I'm going to get a ratio. The derivative goes on top, u prime. So it's going to be 1 minus x squared over 1 plus x squared squared. And I have to divide that by what's in the bottom. So I'm dividing by x over 1 plus x squared. So what I'm going to do is I know that when I divide by a fraction, I've got to keep the first fraction, I've got to change it to multiplication, and I'm going to flip the second fraction. So there's my plus. Sorry, my marker's not working real well. And then I've got the x. So that's simply my u prime, which is right here. There's my u prime. And I'm dividing that by u, which is right there. So because you're dividing by a fraction, I invert to multiply. So this can get simplified. So I'm looking at a common factor. So this is going to reduce with the factor in the denominator, and this in fact would be what my derivative looks like. And this is a really important milestone for us to get to, because now I can look to see where my derivative is equal to 0 and where the derivative does not exist. So we did this with implicit differentiation, that when I get a derivative and it was a rational function, it was important to know that horizontal tangents occur where the numerator is equal to 0, and where my derivative does not exist is going to be where the denominator equals to 0. So what I'm going to do is I'm going to analyze the numerator, and this is really all I have in the numerator. So when I look at that, my critical points, so I'm going to set this, let me just put that in here that I'm setting it equal to 0. So I'm setting it equal to 0. And I'm wondering when that will be true. So let me fix. Okay, so I wanted to be careful of something called a link error. So I'm just running out of room here, so I'm setting the derivative equal to 0. And the reason I'm doing that is I'm trying to find critical points. So where my, let me fix something one more time. Okay, so I've declared what my derivative is, simplified. I've declared that I'm analyzing the derivative, setting it equal to 0. That's a really important step to communicate how you're using the derivative. So now I'm going to state what my critical points are. So my critical points are where the derivative is equal to 0. Alright, so I'm getting plus or minus 1 for where the derivative is equal to 0, solving that equation. And again, I want to pay attention to my domain. X must be greater than 0. So therefore, I'm only going to get one actual candidate out of this pool, and that's going to be where x is equal to 1. And then I look at where my derivative does not exist. So what I'm looking at is where is this derivative not going to exist? And that's going to be at 0 and only 0. There's no other candidate that's going to make that denominator equal to 0. But again, going back to my domain, the domain is x must be greater than 0. So this, in fact, is another place where I'm not getting a critical point that's going to pan out. So I have one candidate only that I'm going to analyze. So now I'm ready to test. So I've constructed a number line, and that's right here. And this is going to be where I show what the derivatives tell me about the function by testing points. So we are going up here. There's my derivative right there. My derivative tells me whether the function's increasing, decreasing, or staying the same. So I'm going to test a value right here in the middle, and I'm going to test 1/2. So when I plug 1/2 into my derivative, I'm getting 1 minus 1/4. That, of course, is a positive value. And when I put in 1/2 into the denominator for x, that's going to be a positive value. So I know with 100% confidence that my derivative is positive on the interval from 0 to 1. My function must be increasing. So now I'm going to do the same thing beyond 1. Now I don't care what number you put in. We'll put in 2. So again, I'm testing a point over here at 2. I'm taking 1 minus 2 squared to get a value for the numerator right here, and that's negative. And I'm going to put in 2, and my denominator, of course, is going to be positive. So a negative divided by a positive is going to give me a negative ratio. What does that mean? That my function must be decreasing. So I only have one critical point, and the domain is from 0 to infinity. So I am really confident that this spot where x is equal to 1 is not just a maximum, but an absolute maximum value. So on your homework, this is really important that you practice. Again, here's your homework. I've kind of condensed it, so do look at the problems that are assigned there. And I really need you to dive into this. And if you do anything, it's really important that you differentiate every function that's given to you. If you're not sure on the steps that you do from there, at least come to class on Monday knowing that we're using derivatives. I need to find that. I need to set it equal to 0. I got to find critical points. I've got to see if there's any endpoints. None of the examples that we've done so far have. So here comes my conclusion, and this is something that's going to again give you points. Finding the derivative, you're going to get a point. Setting it equal to 0, the derivative, you're going to get a point. Finding the critical points, you're going to get a point. Then reaching your conclusion is going to give you that last point. So here we go. F has an absolute maximum value of, I'm going to put f of 1. Now if they want to know what that absolute max value is, okay, let's see if I can write that a little better. At x is equal to 1, and here comes my statement, because the derivative is equal to 0 and it changes the derivative. Okay, so when I say it, I'm being very concise with what I'm writing, and changes signs from positive to negative. And because math is a very symbolic subject, the symbols that I'm using and the way that I'm abbreviating is going to be a way that you can shrink your time and focus on the concepts that you're being taught. So I hope this video helped get another example in. Please try to work on this over break. Go back, let's look at some other things that we need to shore up on. And I'm going to try to get back with everyone soon on how that chapter 3 tests went. So enjoy your vacation and enjoy the food, and I'll look forward to seeing you guys on Monday. And just one last thing that I want to mention here in closing. It's really important that when I declare that there's an absolute max, I'm going to make a note that there are no other candidates to consider. Okay, and I'm just going to abbreviate that there. But we only had one critical point. So because my function was always increasing before 1 and always decreasing after 1, therefore I know that it's an absolute max. Some things to pay attention to for things that we're going to practice in the unit is if it says just a local max, a local min, then I'm not going to find absolute extrema. If they are asking for an absolute max or an absolute min, then it's really important that you declare that you've analyzed every candidate and that you are certain that the candidate that you're proclaiming as the absolute max is because you've looked at every single candidate, and in this case there's only one. But for some other problems that we may encounter in Chapter 4, there may be 2 candidates, so I would have to analyze each candidate if they're both local maxes. Then I would actually go ahead and plug them in and compare their outputs to declare which one ends up being the absolute max. All right, that's it. Take care.